So today, I just talk about the problem of collisionless magnetic reconnection. Oh. So, can you hear me? Green light.
Yeah.
Okay. So, thank you. So this work starts from the joint work with Professor Morrison, and the other people support me to simulate the same problem. And they gave me some numerical code to justify my theory. So this is the introduction. So magnetic reconnection is very well known. So you know it is the change of magnetic field topology like this. So it develops some boundary layer usually like this. So the well-known magnetic reconnection is usually triggered by the resistivity. So I call this the collisional magnetic reconnection because the resistivity is stemming from the collision between ion and electrons. But magnetic reconnection can be also triggered by electron inertia term. So in this case, the reconnection is called collisionless magnetic reconnection because there is no collision and dissipation mechanism. So in any case, there is a role of singular perturbations of ideal magnet hydrodynamics. So I'll talk about this collisionless one. And in the collisionless plasmas, I mean the magnetic Reynolds number is huge. Then the first magnetic reconnections are observed, but their mechanism has not been well understood. So these are two examples. And the tokamak is some toroidal plasma confinement device towards the realization of nuclear fusion power. So the plasma is confined in this torus geometry, but under some conditions there is some linear instability called internal kink tearing instability. And in this case, the core part of the plasma shifts like this. And obviously, this is accompanied by some magnetic reconnection at this boundary layers. And it is believed that this linear instability evolves non-linearly and causes this sawtooth oscillation. This is the experimental result. So we observe very abrupt disruption at in the core region like this. But this collapse is usually faster than predicted by resistive MHD model. So this reconnection should be collisionless magnetic reconnection. But there is no nonlinear theory which explains the fastness of magnetic reconnection. And also in the solar flare, so this collisionless magnetic reconnection is thought to be important because solar flare is driven by this magnetic reconnection like this, and which usually we observe the explosive outflow. But these problems are typical multi-scale problems. So because this boundary layer width is the order of electron skin depth, which is very smaller than the system size. In the tokamak case, the system size is about 1,000 times bigger than this electron skin depth. So the conventional asymptotic matching method has difficulty in analyzing this nonlinear evolution. So linear part is okay, but nonlinear evolution is very difficult to analyze. And also, the direct numerical simulation with this realistic scale separation is still impossible, even by the modern supercomputers. So in this work, by taking advantage of conservative or dissipationless feature of collisionless plasmas, so we employ the variational approach to predict nonlinear evolution. I think this is a new approach, and nobody else tried to apply this variational approach to this such a problem of magnetic reconnection. So this is a model I solved we can call this model two-dimensional MHD model with electron inertia term. And this is the vorticity equation and collisionless Ohm's law. So there is no resistivity in this law. And this term are related to the electron inertia. And this is the singular perturbation of MHD equation. And this bracket is the initial definition of the V bracket. And the electric current is defined by the Laplacian of psi. Psi is the magnetic flux. So there's some special feature in this model. So this model is known as a Hamiltonian system because there is no dissipation mechanism. So Hamiltonian is defined like this. So this is the kinetic energy and the magnetic energy. And this term originally stemming from the kinetic energy of electrons because this is the electric current. And this is the constant of motion of this model. And we can find this Ohm's law can be rewritten like this by defining some special function psi e like this. So physically this represents the electron's canonical momentum. So by defining this psi e, we can easily find this equation, Ohm's law, nothing but the convection of this electron's canonical momentum. So therefore, instead of the magnetic flux psi, this electron's canonical momentum is frozen in flux. So by including the electron inertia term, the topological invariance, it will be slightly modified by this singular perturbation term. So due to this modification of topological invariance, the reconnection is possible without any dissipation mechanism. And in this talk, for simplicity, I will consider only one-dimensional equilibrium state given like this. So I will consider the domain, which is periodic in both x and y directions. And I assume there is no flow in the equilibrium state. And the flux function is given by the cosine function. And this is the equilibrium state. So magnetic field line looks like this. So there is antiparallel field line. And this equilibrium state is found to be unstable, linearly unstable. So the collisionless magnetic reconnection occurs at the boundary layers, which are located at the x equals 0 and plus minus Lx/2 here. And this reconnection is triggered by the unstable eigenmode. And this is the picture of the linear instability. So some reconnection occurs at this point and this point. And so because the magnetic field line looks like the x at this point, so we call this x point. And this is called O point. And these points are essentially equivalent due to the symmetry. And I will assume the wave number in the y direction, k, is sufficiently small. More rigorously, it must satisfy this condition. Then this linear instability is similar to the kink-tearing mode in tokamak. So I will focus on this small wave number regime. And this is the result of direct numerical simulations. So I will always define epsilon as the maximum displacement in the x direction, so which measures the amplitude of perturbation. So these snapshots are taken when epsilon reaches about 4 times dE, the skin depth. So this is the flux function, the x and O point, and this is a corresponding flow pattern. And so the important point is that there is a limitation in the numerical simulation. So because the strong current spike develops at the x point like this, so because there is no dissipation mechanism, so we observe very sharp and strong current spike develops. So the simulation terminates due to the limit of resolution. So we need a lot of grid number to resolve these singular functions. But we can observe numerically the growth of epsilon indeed accelerate when the epsilon exceeds the electron skin depth d, which is this fact is already reported by this paper numerically. So I want to show the proof that this acceleration of magnetic reconnection analytically. So to do that, I first constructed the variational principle, which is nothing but the Lagrangian formulation. So first, let us define G sub t as the flow map, which is mathematically the two-dimensional area-preserving diffeomorphism group. And then the velocity field is defined usually like this, so time derivative of G sub t, and which is related to the stream function like this. And as for the Ohm's law is this one. So we can easily solve this equation provided that the flow map and initial conditions are given. So this we can solve this like this. So by using this relation, we can prescribe the Lagrangian function like this. So this is the so we note that this phi and psi are both related to this flow map by using this relation. So this Lagrangian is a functional of this flow map G sub t. So indeed, if we take the variation with respect to this flow map, then the Euler-Lagrangian equation corresponds to the vorticity equation, which I have already shown here. So this is indeed the Lagrangian for this model. And by comparing with the Hamiltonian function, the only difference is the sign of this and this term. So we can easily find these two terms play the role of potential energy of this system. So intuitively, we can imagine that if the potential energy decreases for some topological fluid motion, then such a motion tends to grow with the release of free energy. So free energy is in this case these two terms. First, so we start from the linear stability analysis. So epsilon is much smaller than the skin depth. So this is nothing but a general procedure. So suppose that we have a given solution and it is perturbed to the phi tilde and psi tilde by the displacement map G sub t. So then we can generally define G sub t as the exponential map like this, and this is the vector field xi and the generator of this displacement, and this must be incompressible vector field. So xi is also, it must be represented by this potential form. Then we can apply the least-least expansion like this, and by substituting this expansion into the Lagrangian, we can perform small amplitude expansion. So at the if we perform the perturbation analysis around the equilibrium state, so this first order automatically vanishes. So the second order quadratic Lagrangian governs the linearized dynamics, and we can prove that it must satisfy this symmetric property. And by assuming the separation of variables like this, which is a very standard linear theory, then we can derive the eigenvalue problem, which is essentially the fourth order ordinary differential equation. It is very difficult to solve this directly, but owing to the existence of a variational principle, we can rewrite this equation into some quadratic form, symmetric quadratic form like this. So this delta W represents the potential energy, and this left-hand side represents the kinetic energy, and the gamma is the growth rate eigenvalue. So there are some positive and negative terms, but in any case, we have to seek the most unstable eigenvalue gamma by minimizing this potential energy while keeping this delta I finite. So this is a application of Rayleigh's method for this problem. Because I don't have enough time, so I give you the only answer. So the final result, the test function that makes delta W negative. So I choose this simple piecewise linear function as the test function. And indeed, this mimics the genuine eigenfunction. And by substituting this piecewise linear function, we can easily reduce the quadratic Lagrangian like this. And this is the potential energy in terms of some normalized variables. The potential energy is evaluated like this. So, and this immediately gives you the linear growth rate gamma like this, and this agrees with our numerical simulation for smaller k, because I assumed small k from the beginning. So this is linear theory, and based on this fact, we move on to the nonlinear analysis. But there's some difficulty in nonlinear analysis because the perturbation analysis is not successful. So this is the previous Dirichlet expansion. But however, we have already seen that the linearly unstable mode has a steep gradient inside the boundary layer. So this piecewise linear function has a steep gradient. So if we differentiate this function, we get to 1 over dE. So each term has the order of epsilon over dE. So this perturbation expansion will not converge when epsilon reaches the skin depth. So in order to study the nonlinear analysis, which is epsilon, in which epsilon is bigger than dE, so we have to perform the fully nonlinear analysis. So without relying on the perturbation expansion, I directly impose the nonlinear displacement map and then evaluate the subsequent potential energy change. So this is again the final answer. So I chose the very special displacement map, which visually looks like this. And there are some key points. So by this displacement, the flux, frozen flux psi E must be contracted around the x point, uniformly contracted. And on the other hand, the flux must be expanded around the O point, and which must satisfy the incompressibility condition. And also, the width L of the intermediate region between expansion and contraction must be taken to be very small, sufficiently small. So we can find only in this intermediate region the potential energy tends to tends to increase. So in order to minimize the potential energy, so this intermediate region must be taken to be small. And then finally, we can find the potential energy decreases in the cubic power of epsilon, which is steeper than the linear regime. So I don't have enough time, so I will almost skip this slide. So this is the schematic view of so this is what's going on in the simulation. So by this displacement, so we obtain very spiky crest in the flux function psi E, and this will be smoothed out by this integral operator. So anyway, so the magnetic energy will decrease in the cubic power of epsilon, and again we observe very spiky structure in the current distribution, but this distribution approached asymptotically to the logarithmic function. This is square integrable, so the current energy is at most the second order in epsilon, so the decrease of magnetic energy is the dominant part. So this is the summary of my analysis and its comparison with direct numerical simulation. So first, I constructed the Lagrangian for this model, and by directly substituting the displacement map, virtual displacement, I reduced the Lagrangian into this form. So in the linear regime, potential energy decreases in the second order of epsilon, which is nothing but exponential growth, linear exponential growth. But in the nonlinear regime, potential energy decreases in the cubic power, and which implies that this epsilon grows explosively in a finite time. And I directly calculated this potential energy in the numerical simulation, and this is a comparison between simulation and this analytical result. This agrees very well. And so, and also, yeah, this model is very simple, but this time scale of the explosion does not contradict the experimental collapse time. This is a summary. So we have performed nonlinear analysis and also simulation of magnetic reconnection driven by electron inertia, and clarified its acceleration mechanism. And by formulating variational principle of a model of collisionless plasma, growth of magnetic island can be predicted by finding a topological deformation of fluid that tends to minimize potential energy of the system. So this is only the same as the before. So in the linear regime, the quadratic potential energy is derived, and the nonlinear regime, the decrease of potential energy is steeper than the linear phase, which gives you explosive growth. And the physical mechanism is a little bit difficult to understand, but most part of magnetic energy flowing into the boundary layer is converted to the kinetic energy. So that's all. Thank you for your attention.
Very much. Questions? Asher.
You introduced a new Hamiltonian formalism which is limited to some kind of symmetry or some kind of assumption. But there are non-Hamiltonian formalism which are general. Why not use a general Hamiltonian formalism? You get perhaps more general perturbations.
General, in what sense general? What do you mean by general?
You make less assumptions. There are many assumptions here.
Yeah.
Be in this form and be in that form. This is limiting.
Yeah, I simplify the problem so much. So this model is already simple one, and also I assumed some geometry, simple geometry. But the analysis, the difficulty is almost result in only boundary layer. So if we change, for example, if we consider another geometry like this, so this boundary layer is equivalent to the model I solved here. So yeah, there are some key parameters, for example, the wave number k, but if we adjust such as key parameters, so these are, I think this result will be universal for other geometry.
The thing is, if you add just two functions, I think you can get a general MHD flow. Ideal, of course.
Yeah, this, you mean this model is too simple, so we have to generalize more complicated model. Yeah.
Well, if you get ideal MHD, you won't get reconnection. So the whole point here, as I understand, is that you get reconnection, which plays a role of removes the barrier to transport.
Yeah.
This is of interest in the tokamak. But the same reconnection does not heat, does it? It does not generate heating, which is another aspect of reconnection that we are interested in very much. But this is the reconnection which does not produce heat.
Yes.
But in reality, when this really happens in the collisionless plasma, would this violent event actually lead to collisions and therefore heating?
Yeah, that would be my future work, but yeah. So.
Andrew, you want
Just
to
one
ask?
quick question. In your simulations, you have initial field and no flow.
Yes.
Would a flow make any difference, or is the whole process too sort of fast for a flow
Yeah.
to do anything?
It's a very nice question. Flow is very difficult. So yeah, if there is initially shear flow, for example, I think yeah, this approach itself may not be successful because using system flow produces some gyroscopic force for perturbation. So even if the potential energy decreases, so we cannot prove the instability.
We can simulate it as well, presumably. You can simulate it as
yeah,
well.
we can simulate, yeah, but analytically it is difficult to understand the mechanism. Yes.
Keith.
For my taste, it seems a very good thing to keep the model as simple as possible.
Yeah,
it's already
it's
quite
possible.
complex, this analysis, and you are focusing on the effect of electron inertia.
Yeah.
And it's good to exclude all other complications and just focus on that one aspect as you have done.
Yeah, but this is my first step, so I want to generalize this model, even including the dissipation mechanism.
More questions, more comments? If not, thank you very much.
Thank you very much.